This video explains some technical terms from the vocabulary of electronic warfare. In this video, we will focus on radar jamming. The video can seem a bit lengthy at first because of the many organograms, but bear with it. You need this information to be considered well informed in a discussion about electronic warfare. Electronic warfare is an element of command and control warfare. Command and control warfare encompasses all the military tactics that use communications technology. It can be abbreviated as C2W. An older name for these tactics is signals warfare, derived from the name given to communications by the military. Newer names include information operations and information warfare. Electronic warfare is defined as the art and science of preserving the use of the electromagnetic spectrum for friendly use while denying its use to the enemy. Electronic warfare consists of three major subdivisions. Electronic warfare support, ES, is the old electronic support measures, ESM. Electronic attack, EA, includes the old electronic countermeasures, ECM. Electronic protection, EP, is the old electronic countermeasures, ECCM. The electromagnetic spectrum ranges from direct current to light and beyond, including the radio frequency spectrum, the infrared spectrum, the optical spectrum, and the ultraviolet spectrum. In summary, electronic warfare involves controlling and manipulating these various frequencies to gain an advantage in military operations. The electronic warfare support or electronic support measures system is designed to detect enemy signals, including both communication and non-communication signals. The signals can either be jammed or their information can be transmitted to other destructive response assets. The received signals can also be used for situational awareness, meaning they help determine the type and location of enemy forces, weapons, or electronic assets. The electronic support system typically collects a large amount of signal data, which allows for less intensive, high-throughput processing. The system then usually only determines which known types of transmitters are present and where they are located. The system takes immediate action against these signals or weapons associated with them. Electronic support is different from signals intelligence. Signals intelligence, abbreviated to SIGINT, is the process of analyzing and identifying intercepted transmissions from sources such as radio and microwave communication, mobile phones, or radar. SIGINT includes communications intelligence, abbreviated to COMINT, and electronic intelligence, abbreviated to ELINT. Although all these areas involve the interception of enemy transmissions, the distinction lies in the purpose for which the transmissions are intercepted. As the complexity of signals increases, the line between these areas becomes increasingly blurred. COMINT receives enemy communication signals. ELINT receives enemy non-communication signals to extract intelligence from the information transmitted by those signals. In summary, SIGINT collects information to determine details of enemy electromagnetic systems to develop countermeasures. ES, or ESM, collects enemy signals, both communicating and non-communicating, to take immediate action on the signals or weapons associated with those signals. For a long time, jamming was known as electromagnetic countermeasures, abbreviated to ECM, but now it is referred to as electronic attack in literature, abbreviated to EA. Radar jamming and deception is a form of electronic attack in which radio frequency signals are intentionally emitted to interfere with the operation of the radar by saturating the receiver with noise or false information. Concepts that overlay the radar with signals, so its display is no longer readable, are usually called jamming. In contrast, systems that generate confusing or conflicting signals are called deception. Jamming is sometimes called soft kill because it temporarily disables an enemy asset without destroying it. The objective of jamming is to disrupt the enemy's effective use of the electromagnetic spectrum. This spectrum is used for transmitting information between different points, in the form of voice or non-voice, such as video or digital format, communication, command signals for controlling remotely stationed assets. Data obtained from remotely stationed equipment, or for tracking friendly or enemy assets, land, sea, or air. Electromagnetic countermeasures include jamming for self-protection, remote jamming to protect other assets, chaff, flares, and decoys, to interfere with the operation of radars, military communication, and heat-seeking weapons. Anti-radiation weapons were not part of EU then. The common definition is now. Electronic attack also involves using high levels of radiated power or directed energy to physically damage enemy assets. There are 4 classes of electronic attack: jamming, modifiers, radar-absorbing materials, and physical destruction. The jamming can be classified in different ways. The type of signal is determined by whether it is directed against a pulsed radar or against continuously transmitting communication channels. The way of attacking differs in the aim of the jamming. This is intended to mask one's own actions or to deceive the enemy about one's own intentions. The jamming geometry distinguishes between different constellations where the jammer is located and by the way how it protects a friendly asset. Additionally, besides the traditional electronic measures, there is also mechanical jamming. We will discuss these possibilities in this order. However, some technical terms need to be defined to find a common language. The most effective measure of electronic attack is active noise jamming. In any case, this worsens the signal-to-noise ratio in the radar receiver and thus the probability of detection of the radar. It's important to remember that you need to jam the receiver, not the transmitter. Example given: it is not practical to jam the interrogator of a secondary radar since it would require a significant amount of jamming power. The transmitter operates at 1030 MHz, while the transponders operate at 1090 MHz. The only thing a jamming transmitter can do is interfere with the sensitive receivers by either driving them into saturation or constantly transmitting interfering phase jumps to prevent the decoding of the signals. The exception is when the transponders of aircraft are to be jammed. They can then no longer respond to the interrogations of the secondary radar and the enemy radar can no longer distinguish between friend or foe. The jamming-to-signal ratio is the ratio of the power received from the jamming signal transmitted, J, to the power received, S, from the radar backscatter from the target. This ratio is calculated by comparing the power density of the jamming signal to that of the desired signal. Logarithmic scales are often used. The specifications are therefore converted into decibels. In the simplest case, we assume that it is a monostatic radar and that the jamming equipment is located on the target. The receiving and transmitting antennas of the radar are arranged next to each other, ensuring that the ranges and free space loss factors for the outward and return paths are the same. The linear strength of the received jamming signal, J, is determined by the one-way radar range equation. The transmission power and the antenna gain of the jamming equipment, the antenna gain of the radar, and, of course, the wavelength-dependent free space loss for the single range between the jammer and the radar all have an effect. The strength of the echo signal, S, is determined by the two-way radar basic equation, for which I created a separate video. The link to this video can be found in the video's description. The jamming-to-signal ratio is the ratio of the power received from the jamming signal transmitted to the power received from the radar backscatter from the target. This ratio is calculated by comparing the power density of the jamming signal to that of the desired echo signal. The transmitted power at the antenna can be grouped with its antenna gain. EIRP is the effective isotropic radiated power and means the multiplication of the transmitted power measured at the antenna with the antenna's gain. The burn-through range is the radar-to-target range where the target echo signal can first be detected through the electronic attack. The free space path loss for the radar signal, due to the additional return path, is proportional to the fourth root, while the jamming signal for the single distance decreases with the square root. At some point, the radar's transmission power becomes higher compared to the jamming power and the radar recognizes the target despite the jamming. There are two main forms of jamming techniques, spot and barrage jamming. Spot jamming is concentrated power directed toward one channel or frequency and is usually quite effective if the radar cannot use frequency hopping. Barrage jamming, sometimes called splash jamming, is where a single wide bandwidth transmitter is used to jam a specific range of adjacent frequencies. Swept jamming is a kind of spot jamming in which a narrow frequency band of jamming energy is repeatedly swept over a relatively wide frequency band. The sweep rate is such as to be on any given frequency only long enough to accomplish its jamming task, returning to that frequency again before the expiration of the jammed circuit recovery time. Sweep jamming combines the advantages of both spot and barrage jamming by the rapid electronic sweeping of a narrow band of jamming signals over a broad frequency spectrum. The disadvantage of sweep jamming is its high susceptibility to electronic protective measures. Jamming signals can be categorized into radar signals and communication signals. The primary difference between radar and communication jamming is in the geometry. Despite their different purposes, these two types of jamming signals can share similar parameters. Radar signals can be either pulsed or continuous, while communication signals are mostly continuous. Radar signals are generally in the microwave frequency range but can also be in the low or high VHF range and can even extend into the millimeter range. Communication signals can transmit either voice or data and are typically found in the HF, VHF, or UHF bands. However, they can also exist in the VLF and millimeter wave range. Communication signals include both voice communication and digital data transmission. For example, links between unmanned aerial vehicles, UAVs, and their control stations are typical digital data links. Communications jamming, abbreviated to COMJAM, refers to the deliberate interference of communication signals. Typically, this involves tactical HF, VHF, and UHF signals using noise-modulated cover jamming. However, it can also include jamming point-to-point microwave communications links or command and data links to and from remote assets. Note that you can only jam the receiver. The enemy's communications link carries a signal from a transmitter to a receiver. The jammer also transmits enough power into the receiver's antenna to overcome the disadvantage of the antenna's side lobe gain, if the receiving antenna has a narrow beam and is pointed at the transmitter. This interference is received and output to the receiver's operator or processor with enough power to reduce the quality of the desired information to an unusable level. EIRPJ means the jammer and EIRPS means the value of the signal's transmitter. GM is the main lobe gain of the receiving antenna. GS is the average gain of the receiving antenna's side lobes. RT is the distance transmitter to the target. RJ is the distance jammer to the target. The difference between the main and side lobes is only crucial for directional radio links like satellite communication. Small handheld walkie-talkies use an omnidirectional antenna. Therefore, both antenna gains can be omitted in the equation. A classical radar consists of a transmitter and a receiver, both of which use the same directional antenna. The receiver is designed to optimally receive echo signals from objects illuminated by the radar transmitter. By analyzing the return signals, the radar can determine the location and velocity of a land, sea, or air asset, and track it for friendly purposes such as air traffic control, or unfriendly purposes such as an attack by guided missiles or guns. A radar jammer provides either a cover or a deceptive signal to prevent the radar from locating or tracking its target. Jamming can be divided into two methods, known as concealment or masking. Masking usually uses some form of noise as the transmitted jamming signal. Jamming can be achieved by transmitting high-power signals to an enemy receiver. By using noise modulation, it becomes difficult for the enemy to detect the jamming. This lowers the enemy's signal-to-noise ratio, SNR. to a level where they cannot receive the desired signal with sufficient quality. The figures illustrate a radar plan position indicator, PPI, scope screen with a return signal and noise cover jamming that is strong enough to hide the return. In an ideal scenario, the jamming should be powerful enough to make it impossible for a trained operator to detect the signal presence. However, if it is not practical to achieve that level of jamming power, reducing the SNR level is sufficient to prevent automatic tracking. Automatic processing requires a better SNR than what is required for a trained operator to manually detect and track a signal. The aim of concealment is to imitate the radar's probing signal and create a false image of the threat situation. Concealment or deception might be better called forgery. During deception, false target signals are generated which the radar receiver accepts and processes as real targets. Deceptive jamming causes a radar to draw incorrect conclusions from its desired signal and the jamming signal, as shown in the lower figure. This kind of pulsed jamming can mislead the radar from the target in range, angle, or velocity. With deceptive jamming, the radar receives a valid return signal and mistakenly believes it is tracking a valid target. Repeater jamming is a type of deception that relies on confusing or deceiving a radar system, causing it to display false information. This technique involves sending back a boosted version of the signal received from the radar, which is stronger than the radar's own signal and captures the radar's range gate. In most cases, additional target signs are generated at different ranges so the radar cannot detect the real target. Jamming can also be classified by jamming geometry, which means, according to the position of the jamming carrier to the object to be protected. In self-protection jamming, the radar echo source and jammer are collocated. In remote jamming, the equipment is located in another aircraft. Escort jamming means the jammer is located in another aircraft at a slightly different angle and/or range. If the escort platform is sufficiently close to the target, within the beam width of the radar's main lobe, the jamming to signal calculations are the same as for self-protection jamming. In support jamming or side lobe jamming, a jammer in a different platform is used to protect other platforms or fulfill other mission requirements. In stand-in jamming, the distance of the supporting jammer to the radar is smaller, and at standoff jamming is the distance to the radar larger than the distance of the aircraft to be protected. With main lobe jamming, the jammer platform and the target must both be in the main lobe of the radar when it scans the airspace. This can happen during self-protection jamming as well as during escort jamming. Since the echo signal and interference are subject to the same antenna gain of the radar's side lobe attenuation can be omitted from the general equations. With support jamming, the signal and jamming have a different antenna gain at the radar. In this case, the jammer must compensate for the side lobe attenuation by increasing the transmitting power. A larger transmission power is needed to cover longer distances during standoff jamming. A jammer can generate relatively large effective radiated power. This technique involves just increasing the jammer power by enough to overcome the processing gain in the receiver. For the same effect, the jammer requires less transmission power but is within the enemy's weapon range at stand-in jamming. This situation is often achieved by deploying mobile ground-based jamming equipment. In the past, the direction from which the jamming was transmitted could be determined based on the jamming signal strength. Modern jamming equipment measures the horizontal antenna pattern of the radar antenna and modulates its jamming signal strength in the opposite direction to this pattern. As a result, the direction of arrival of the jamming can no longer be determined. This is a particularly good example of using electronic support. Here the reconnaissance of the horizontal antenna pattern, for an immediate reaction. Let's remember the definition shown at the beginning of the video. Jamming is the deliberate radiation, re-radiation, or reflection of electromagnetic energy to impair the use of the enemy's equipment. Mechanical jamming refers to additional reflections. Dummies are fake military equipment and often just optical imitations to deceive the enemy. Mechanical jamming is when these dummies are reduced to reflection properties like the originals that are to be imaged. These dummies are then called decoys. Here in the picture is an inflatable decoy that simulates a larger ship. Flares are infrared countermeasures that protect target platforms against heat-seeking missile threats. Chaff is a radar countermeasure in which a cloud of small, thin pieces of aluminum, metallized fiberglass, or metallized plastic is distributed, creating additional interfering echo signals on the screen. Half-wave dipoles are especially effective as radar reflectors. Typically, to counter a 10 GHz radar, the dimensions of the chaff dipoles would be 0.6 inches long, 0.01 inches wide, and 0.001 inches thick. Just 1 pound of chaff is needed to produce an echo the size of a large bomber. Numerous dipoles are packed tightly into small containers. When these chaff packets are released into the air vortex behind the aircraft, they burst open and disperse, creating a cloud of chaff that interferes with radar signals, called a chaff corridor. Chaff falls slowly, often taking many hours to reach the ground, and it moves with the wind speed, which can therefore also cause a Doppler frequency. This means that this jamming remains visible despite moving target indication. An example of the application is the AN/ALE55 fiber optic towed decoy, abbreviated to FOTD. It is an electronic attack measure developed by BAE Systems Electronic Solutions for the F-18E Super Hornet. It provides 3 layers of self-protection jamming against a radar-based threat. It prevents radar tracking, disrupts radar locks, and serves as a boosted target for incoming missiles. The Sky Shield Escort Jammer from the Rafael Company is a standard military solution that has already been delivered to several customers worldwide. It uses active electronically scanned array technology, abbreviated to AESA, and offers a highly effective radiated power in a desired direction with its single broadband jammer. I hope you enjoyed this video. Thank you for your attention. The screenshots of jammed radar sets were taken during the NATO exercise Elite 2007 at the Heuberg training area on radar sets P-18, Spoonrest D, and ST-68U, tin shield of the Hungarian Army. Jamming was carried out using the jam car jamming device developed by the former Luftwaffenwerft 51, which utilized commercially available signal generators and power amplifiers, along with a self-developed power modulator.